Hello friends, welcome to this video introducing Booth's algorithm approach in binary multiplication. The objective of this video is to explain the concept of Booth's algorithm for binary multiplication. In the previous videos of this set of videos dedicated to the binary multiplication, we have presented two methods: the basic binary multiplication method and the partial sum approach method. Also, we have explained what is a partial product, what is a shift, and how many additions are necessary to perform a multiplication. So, in the basic binary multiplication, the number of partial products is n to the power 2, the number of shifts is equal to the number of bits, and the number of additions is 2 times the number of bits. In the partial sum approach, the number of partial products and the number of shifts are also the same, but the number of additions depends on the number of ones in the multiplier, which makes this process better in the case that the number of ones is less than the number of bits. Now, in this session, we are going to introduce the concept of Booth's algorithm to understand how the use of this new algorithm can further increase the efficiency of the multiplication process. Please keep in mind these shifts and additions, because afterwards we will compare them in the case of Booth's algorithm, so to determine the increase of efficiency we can obtain using this algorithm. Let's now dive into the concept of Booth's algorithm. The Booth algorithm says that decoding a binary number into decimal can be obtained by using the algorithm 2 to the power p plus 1 minus 2 to the power q, where p is the bit where the series of 1 start and q the bit where the series of 1 finish. When there are several series of 1, the algorithm can be written as the sum of 2 to the power p plus 1 minus 2 to the power q. Remember that decoding a binary number means converting it to decimal or to another desired format. Let's explain that. Suppose that we have a binary number made with a sequence of ones having some leading and succeeding zeros. It has been found that in this case the conversion of a binary number into decimal can be done in a way better than the traditional way. Let's see an example. Suppose that this is the number that contains this series of ones. In the traditional conversion, we do this and we obtain 62. But with the new Booth's algorithm, the coding is much shorter. This is the algorithm. This is 5 because the bit where the series start is the 5th. 0, 1, 2, 3, 4, 5. And this is 1 because the bit where the series finish is the 1st. So we obtain the result faster, and it is 62. Let's see another example where not all ones are continuous. Here we have two series of ones, this and this. This is the traditional conversion, and we obtain 110. Applying the new Booth's algorithm, this is the first series of ones, and this is the other series of ones. The result is 110, so it is correct. So note that this method also works when the series of ones are distributed in several sequences. In this case, the result is the addition of the several sequences. Now, let's go on a step forward and let's apply this Booth algorithm to a binary multiplication. For example, the multiplication of m times q, where the multiplicand is 0, 1, 0, 1, 1, and the multiplier is 0, 1, 1, 1, 0. Note that for the multiplicand I have chosen any number, but for the multiplier I have chosen a number made by a sequence of ones having a leading 0 and a succeeding 0. Let's proceed to perform the multiplication. Applying the Booth's algorithm to the multiplier, we have the first one is in the place 3 and the last one is in the place 1. So the algorithm is 2 to the power 3 plus 1 minus 2 to the power 1. Performing the multiplication, we have this. Note that we have converted a subtraction into an addition by using the 2's complement. Now, let's calculate each term. 2 to the power 4 m means we shift 4 times, so we add 4 zeros. 2 to the power 1 2's complements means we find the 2's complement and we shift 1 time, so we add 1 zero. This is the 2's complement, and we add 1 zero. Note that we extend this number to 9 bits to align the number of bits to the first term. Remember that extending the number is repeating the sign bit of the number several times in front of the sign number. Remember also that with the sign extension, the value of the number remains the same. And now, making the sum, we have this result. The sum is correct because you can verify by yourself that this number in decimal is 154, so it is correct. If you review the operations that we have just made, you will find that in the case of the Booth's algorithm, we have made 5 shifts. 4 shifts to the left for the term 2 to the power 4 m, and 1 shift to the left for the term of the 2's complement. And the number of additions we have made are 2. 1 addition to add 1 to make the 2's complement, and 1 final addition to add the 2 terms. Now, comparing with the partial sum approach, to perform the same multiplication, the number of shifts we would need will be equal to the number of bits, so it is 5. And the number of additions will be equal to the number of ones in the multiplier, so in this case it is 3. So this is the table. As you see, the number of additions needed in the case of the Booth's algorithm is less. In summary, this represents the Booth's algorithm for multiplication. Note that this is the multiplier, with a series of ones. And these are P and Q. I emphasize again that the Booth's algorithm stresses the format of the multiplier Q, but the multiplicand M can be any number, including or not a series sequence of ones. And these are the main conclusions of this presentation. In summary, the Booth decoding algorithm can efficiently reduce the number of additions during the multiplication. This number of additions depends on how the series of ones in the multiplier are distributed in sequence. The use of the algorithm is focused only in the multiplier. The most advantage is obtained when the multiplier has a sequence of ones in series between some leading and succeeding zeros. Compared to the partial sum approach method, in the Booth decoding algorithm, the number of shifts are similar. However, the number of additions gets actually reduced. I hope also that on the way along this video you learn that applying a 2's complement we can convert a subtraction into an addition. That to extend the bits of a binary number we have to repeat the most significant bit to the front of the number, and that with the sign extension the value of the number remains the same. And to shift the bit sequence toward the left and add k zeros on the right, we need to multiply the binary number by 2 to the power k. That's all for today. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos. In the next video, we will present the practical implementation of Booth's algorithm.